And as night falls, suddenly two moth-like creatures come out of the forest. They are headed directly for the buildings. Let's roll for initiative. Go.
Physicists from all over the world come to Denver, Colorado. Theory?
Hey, wait, is that you?
Hi, yeah, my name's Clara.
Nice to meet you, I'm Maya.
Oh, nice to meet you, Maya. So I'm a particle physicist.
So cool.
Yeah, nice. What are you working on?
I work on spin squeezing and strontium optical lattice clocks.
Oh, nice. I haven't seen any talks on that this week and I'd really love to learn more. Could you tell me about your research?
I would love to. I'm actually supposed to go play this tabletop RPG STEM game right now. Do you want to come join?
I would love to. That sounds great. Thanks. I'm Clara Nellist, physicist, and I deal cold damage by exposing them to the void of outer space.
You all have arrived at the village of Linnaeus. You are agents of the Noether Society, sent here by Professor Emmy Noether herself. Apparently there was an attack last night on these three buildings at the northern edge of town. The mayor just wants you to figure out what's gone on here.
Do the size of the tracks sort of match up with the scale of the damage?
That's what's interesting.
Is there any iridescence of the scales? Do they reflect light?
If your hypothesis is relevant to the creatures you fight, you start combat with a bonus flow point.
Yeah, some kind of creature took these bites. Something is consuming these.
Can I form a hypothesis
I'd love for you to form a hypothesis.
that these creatures are defending the woods?
Suddenly, out of the woods comes a large-sized creature and a medium-sized creature. They shout, "For the safety of the forest!" All three of your hypotheses are relevant. You all start combat with a bonus flow point.
Nat 20!
Nat 20 on initiative. Very nice, very nice. All right. He's gonna do a buzzing wing attack.
As an astrophysicist, do we have any lights? Is there a moon?
And it is our engineer's turn.
I'm gonna prototype some kind of like ambulatory torch.
We come to our mathematician Shree's turn.
I'd like to posit that it has some sort of light sensitivity.
That is an unnatural 20, and that is a hit. Do confirm, yes, they are severely distracted by light, because this one was like looking around the mathematician. Let me at it, let me at it.
Can I use a force blast to send the light source back
I
into
think
the
that's
forest?
a great idea. 18 on the die is a perfect. You manage to swerve it around. One of them turns around and warns you. You have won this day, but we will return. The Mothman will have what is owed. But you have saved the village for today. Congratulations.
Okay.
Good teamwork.
Yeah.
Amazing.
Let's go.
Go science. That was so much fun. Thank you for inviting me.
Oh, I have so much fun playing games like this. I think it's because it taps into like the probability of all of these outcomes happening.
Yeah, maybe we could measure the statistical probability of me getting that many nat ones.
Yeah, your dice is just cursed or something.
Yeah.
Well, or this coin even. You know, if you're trying to measure if a coin is fair like this, it takes a lot of flips to be able to resolve it. But working with atoms, we can always use quantum entanglement properties like spin squeezing to make this sort of measurements more precise.
So this is exactly your research, right?
It's pretty relevant.
Great. So how could we know, for example, if a coin is biased?
Yeah. So if you're flipping this coin, it only has two discrete outcomes, right? Heads or tails.
Yeah.
And it's the same actually when we're measuring atoms. I work with strontium optical lattice clocks where we're interrogating tens of thousands of identical atoms. And we want to make measurements of them in order to learn about the environment, the laser, other things around them.
So the environment of the clock.
Exactly. But the fundamental noise source for these systems is the fact that each time we read out an atom, we only get one bit of information, just like if you flip that coin and it's only heads up or heads down.
So you're collapsing it could be either heads up or heads down, and then when you're observing it, you're collapsing it.
That's exactly right.
But are the atoms entangled then?
Well, so that's where we can win.
Okay.
If we can generate entanglement between the atoms in our sample, then the sort of normal noise that you get from this coin flipping process scales like the law of large numbers. So square root n is the precision of your measurement. It gets better as you keep flipping coins. But if we can engineer entanglement in our system, then we get better collective scaling. So for flipping n coins, the fundamental limit can actually scale like n instead of square root of n. So you can get a quantum speed up.
So I wouldn't have to flip the coin as many times to know if it was biased.
Exactly. In fact, with the amount of squeezing we generate in our setup, you could make a measurement about twice as fast.
Great. So why do you need your atomic clocks to be so precise?
That's a fantastic question. These systems are really, really powerful tools, not just for timekeeping, but also for understanding the fundamental physics affecting them. One really cool measurement that our lab has been able to do is looking at a cloud of strontium atoms in Earth's gravitational potential. There's an effect from general relativity, which is called a gravitational redshift.
Yeah.
And we can observe this effect. Typically, when we think of general relativity, we're thinking on like galactic scales, right? But we can observe this across a 1 millimeter sample in Earth's gravitational potential.
This is an incredibly precise measurement in and of itself, but is there any other use for this kind of work?
Yeah, absolutely. So atomic clocks also underpin a lot of technology that people probably use all the time. So GPS on your phone works by pinging the signal off to different satellites and timing how long it takes to come back. So the more precise your time measurement, the better you can triangulate your spatial position. People are also really interested in using these systems to do measurements of local gravity, which could be used to find groundwater, for example, which will be important.
Yeah, I think a lot of people don't realize that they rely on Einstein's general relativity in order to get around. I mean, I use GPS all the time now to navigate, and it's so important to our day-to-day lives, but these kind of really precise physics measurements can then improve the accuracy of those systems.
It's exactly right.
How have you been finding the conference while you've been here? Didn't you get the bus? You're lucky.
Yeah, I'm right next door. It's been really, really lovely having it here and getting to see so many friends from former physics programs and having crossed paths all over the place. I think one thing that's really fun is how large it is. So I get to find out more physics from further outside of my field than I often would get to. So I'm, of course, attending a bunch of atomic physics talks, but I also get to hear about superconducting qubits and all sorts of other fun fields that people are exploring.
Wonderful. Well, thanks for talking with me. Thanks for inviting me to the game, and I will see you at the next one.
See you at the next one.
Great.